Hello everyone, let me introduce myself first. My name is Infantri Siahaan, and I am a mechanical engineering student from Udayana University. And now I want to presenting about non-ferrous metals, a variety of possibilities. So this is the topic that I want to presenting, and the main reference I took from Metalurgi for the non-metallurgist second edition by Arthur C. Riordan. Okay, the first material is light metals like aluminum, BAMG, and Ti. High-strength, lightweight alloys are crucial for engineering application across land, sea, air, and space transportation. Reducing the weight of the system by just 1 kilogram can significantly decrease the weight of power plants, transmission system, and overall fuel consumption. Consequently, there is a significant demand for high-strength, lightweight metals and alloys. Light metals, typically defined as having a density lower than steel, are sought after for their specialized properties suitable for these advanced engineering needs. Next is corrosion-resistant alloys like cobalt, nickel, titanium, and aluminum. Non-ferrous metals and alloys are extensively utilized in corrosive environments, ranging from water piping and food preparation to essential components in chemical plants, handling aggressive acids and alkalis. These materials are often chosen over steels and stainless steels for several reasons. First, the diverse range of non-ferrous metals and alloys offers physical and mechanical properties, such as a high strength-to-weight ratio of superior thermal and electrical conductivity, which can be advantageous compared to ferrous alloys. Second, many non-ferrous metals and alloys exhibit significantly higher corrosion resistance than most alloy steels and stainless steel grades. Common examples of non-ferrous metals known for their excellent corrosion resistance include copper, nickel, titanium, and aluminum. Superalloys. Superalloys are a group of nickel-based, cobalt-based, and iron-nickel-based alloys that exhibit outstanding strength and surface stability at temperature up to 85% of their melting points, expressed in degrees Kelvin. The iron-nickel-based superalloys are an extension of stainless steel technology and generally are rock, brass, cobalt-based, and nickel-based superalloys may be raw or cast depending on the application or composition involved. Cast single crystal forms are often produced for aircraft applications. Superalloys are generally used at temperature above 540 degrees Celsius or above 1000 degrees Fahrenheit. They were initially developed for use in aircraft piston engine turbo superchargers. Next is corrosion resistance alloys. Oh wait, my bad. Next is refractory metals. This group of metals consists of niobium, also known as columbium, tantalum, molybdenum, tungsten, and rhenium. Aside from two platinum group metals, osmium and indium, refractory metals boast the highest melting temperatures among all metals. Tungsten in particular has the highest melting point of any element at 3410 degrees Celsius. Despite their impressive melting points, refractory metals are prone to degradation in oxidizing environments at relatively low temperatures, limiting their use to low temperature or non-oxidizing high temperature settings. However, the development of protective coating system, especially for niobium, has expanded their applicability to high temperature oxidizing environment in space. Historically, their use was confined to lamp filaments, electron tube grids, heating elements, and electrical contacts. Nowadays, refractory metals are also employed in the aerospace, electronic, nuclear, and chemical processing industries. Next is low melting point metals. Bismuth or B is a brittle metal that is easy to cast but not easily shaped using standard working methods. It has a melting point of 183 degrees Celsius, which is lower than that of thin lead solder. Uniquely, bismuth is one of the few metals that expand upon solidification. It is diamagnetic, meaning it is slightly repelled by magnetic fields, and has a low capture cross-section for thermal neutrons. Alloys with low melting points such as the BCD in alloy, which melt at 47 degrees Celsius, are known as fusible alloys and are used in applications like sprinkler system triggering device. In nuclear research, bismuth's high density provides excellent gamma ray shielding, while its low neutron cross-section permits the passage of neutrons. Additionally, small amounts of bismuth, like 0.1%, add to iron and steel enhance their machinability and mechanical properties. Reactive metals. Reactive metals usually combine with oxygen at high temperature to form very stable oxides and are considered extremely noble due to their passive films. However, they can become brittle by absorbing interstitial elements like oxygen, hydrogen, and nitrogen. Reactive metals such as niobium, tantalum, zirconium, and titanium are quickly attacked by hydrofluoric or HF acid, whether in their pure form or as alloys. Even small amounts, 1 or 2% of reactive metals in stainless or nickel alloys can significantly reduce their resistance to hydrofluoric corrosion. The group of reactive metals includes beryllium, titanium, niobium, tantalum, hafnium, and zirconium. Beryllium and titanium, being low-density metals, are often used in light structural application. Niobium and tantalum, known for their high melting points, are also categorized as refractory metals. Next is precious metals. This family includes egg metal, with gold and silver being the most well-known. Less familiar are the 6 platinum group metals, which often occur together in nature: platinum, palladium, iridium, rhodium, ruthenium, and osmium. Gold or aurum is notably soft, ductile, and easy to deform. Chemically, pure gold is 99.9% pure, with even higher purities available commercially. Its most remarkable property is its resistance to oxidation, allowing it to maintain its yellow color in air and when heated. Due to its softness, gold is typically alloyed to increase its hardness, making it suitable for common applications like jewelry. The largest use of gold is in jewelry and the arts, followed by industrial applications, mainly in electronics and then dentistry. Historically, gold's primary use was monetary, but this has now dropped to less than 1%. Alloys such as aurum, silver, and cuprum can produce a range of colors, from white to various shades of yellow. Rare earth metals. The 17 rare earth elements form a closely related group of highly reactive metals, which readily combine with oxygen at high temperature to form stable oxides. These reactive metals like titanium, zirconium, and beryllium can become brittle by absorbing oxygen, hydrogen, and nitrogen interstitially. The term rare earth is misleading because these elements are not actually rare. The name comes from the oxide mineral in which they were first found. The rare earth family includes scandium, yttrium, tantalum, cerium, praseodymium, neodymium, promethium, samarium, europium, gadolinium, terbium, dysprosium, and another muum. This metal, an alloy of the cerium group, is the least expensive rare earth alloy. Next is metalloids or semi-metals. There are some elements that act as metals under some circumstance and act like non-metals under different circumstance. These are now called semi-metals, but have been called metalloids like metals. These elements tend to be semiconductor. Silicon is an important example. Other examples include boron, gallium, germanium, arsenic, antimony, tellurium, polonium, and astatine. Okay, I think this is the last topic, that is special purpose metals and alloys. Uranium is a moderately strong and ductile metal that can be cast, formed, and welded using various standard methods. It is primarily used in non-nuclear application due to its high density, which is 68% greater than that of lead. However, uranium and its alloys are generally considered difficult to machine, requiring specialized tools and conditions. Depleted uranium is processed, melted, fabricated, and machined using conventional metallurgical techniques, but special precautions are necessary due to its radioactivity, chemical toxicity, and pyrophoric nature. Its toxicity is akin to that of other heavy metals, but its pyroporicity means that powder or chips can spontaneously ignite when exposed to oxygen. Inhalation of excessive dust or fumes can lead to health issues, including kidney damage. Uranium is often chosen over other dense material because it is easier to cast and fabricate than tungsten and is less expensive than gold or platinum. Common non-nuclear applications for uranium and its alloys include radiation shields, counterweights, and armor-piercing ammunition for tank-mounted cannons. Okay, that's all I can tell to all of you about this topic, and I say thank you for your attention.